Ethernet was originally based on the idea of computers communicating over a shared coaxial cable, acting as a broadcast transmission medium. The methods used were similar to those used in radio systems, with the common cable providing the communication channel likened to the luminiferous ethers in 19th century physics, and it was from the reference that the name Ethernet was derived. Original Ethernet's shared coaxial cable traversed a building or campus to every attached machine. A scam known as carrier sense multiple access with collision detection governed the way the computers shared the channel. This scam was supplier than the competing token ring or token bus technologies. Computers were connected to an attachment unit interface, AUI transceiver, which was in turn connected to the cable. Later, with thin Ethernet, the transceiver was integrated into the network adapter. While a simple passive wire was highly reliable for small networks, it was not reliable for large extended networks where damage to the wire in a single place or a single bad connector could make the whole Ethernet segment unusable. Through the first half of the 1980s, Ethernet 10-base-5 implementation used a coaxial cable 0.375 inches or 9.5 millimeters in diameter, later called thick Ethernet or thicknet. Its successor, 10-base-2, called thin Ethernet or thinnet, used a cable similar to cable television of the era. The emphasis was on making installation of the cable easier and less costly. Since all communications happen on the same wire, any information sent by one computer is received by all, even that information is intended for just one destination. The network interface card interrupts the CPU only when applicable packets are received. The card ignores information not addressed to it. Use of single cable also means that the bandwidth is shared, such that, for example, available bandwidth to each device is halved than when two stations are simultaneously active. Collisions corrupt transmitted data and require stations to retransmit. The lost data and retransmissions reduce throughput. In the worst case, where multiple active hosts connected with maximum allowed cable length attempt to transmit many short frames, excessive collisions can reduce throughput dramatically. However, a Xerox report in 1980 studied performance of an existing Ethernet installation under both normal and artificially generated heavy load. The report claims that 98% throughput on the LAN was observed. This is in contrast with token passing LANs, token ring or token bus. all of which suffer throughput degradation as each new mode comes into the LAN due to token weights. This report was controversial, as modeling showed that collision-based networks theoretically became unstable under loads as low as 38% of nominal capacity. Many early researchers failed to understand these results. Performance on real networks is significantly better. The 10BASE-T standard introduced a collision-free, full duplex mode operation that eliminates collisions. Modern elements are entirely collision-free. Talking about the Ethernet, we need to mention the devices briefly, because we talked about these devices more deeply before. But we will look to that device very briefly, including our knowledge about the Ethernet. For signal degradation and timing reasons, coaxial Ethernet segments had a restricted size. Somewhat larger networks could be built by using an Ethernet repeater. Early repeaters had only 2 ports, allowing at most a doubling of network size. Once repeaters with more than 2 ports become available, it was possible to wire the network in a star topology. Early experiments with star topologies called FiberNet using optical fiber were published by 1978. Shared cable Ethernet was always hard to install in offices because its bus topology was in conflict with the star topology cable plans designed into buildings for telephony. Modifying Ethernet to conform to twisted pair telephone wiring already installed in commercial buildings provided another opportunity to lower costs, expand the installed base, and leverage building design, and thus twisted pair Ethernet was the next logical development in the middle of 1980s. Ethernet on unshielded twisted pair cables, or UDP, began with StarLAN at 1 megabit per second in the middle of 1980s. In 1987, Synoptics introduced the first twisted pair Ethernet at 10 megabit per second in a star-wired cabling topology with a central hub, later called LatticeNet. They evolved into 10BASE-T, which was designed for point-to-point links only, and all termination was built into the device. This changed repeaters from a specialist device used at the center of large network to a device that every twisted pair-based network with more than 2 machines had to use. The tree structure that resulted from this made Ethernet networks easier to maintain by preventing most faults with one pair or its associated cable from affecting other devices on the network. Despite the physical star topology and the presence of separate transmit and receive channels. In the twisted pair and fiber media, repeater-based Ethernet networks still use half-duplex and CSMA-CD or carrier sense multiple access collision detection with only minimal activity by the repeater. Primarily the collision enforcement signal in dealing with packet collisions. Every packet is sent to every port on the repeater, so bandwidth and security problems are not addressed. The total throughput of the repeater is limited to that of the single link, and all links must operate at the same speed. While repeaters could isolate some aspects of Ethernet segments, such as cable breakages, they still forwarded all traffic to all Ethernet devices. This created practical limits on how many machines could communicate on an Ethernet network. The entire network was one collision domain, and all hosts had to be able to detect collisions anywhere on the network. This limited the number of repeaters between the farthest nodes. Segments joined by the repeaters had to all operate at the same speed, making phased-in upgrades impossible. To alleviate these problems, bridging was created to communicate at the data link layer while isolating the physical layer. With bridging, only well-formed Ethernet packets are forwarded from one Ethernet segment to another. Collisions and packets error are isolated in this case. Prior to learning the network devices on the different segments, Ethernet bridges and switches work somewhat like Ethernet repeaters, passing all traffic between segments. After the bridge learns the addresses associated with each port, it forwards network traffic only to the necessary segment, improving overall performance. Broadcast traffic is still forwarded to all network segments. Bridges also overcome the limits on total segments between two hosts and allowed the mixing of speeds, both of which are critical to deployment of fast Ethernet. In 1989, the networking company Kalpana introduced the Ether switch, the first Ethernet switch. This worked somewhat differently from the Ethernet bridge, where only the header of the incoming packet would be examined before it was either dropped or forwarded to another segment. This greatly reduced the forwarding latency and the processing load on the network device. One drawback of this cut-through switching method was the packets that had been corrupted would still be propagated through the network, so a jabbering station could continue to disrupt the entire network. The eventual remedy for this was a return to the original store and forward approach of bridging, where the packet would be read into the buffer on the switch on its entirely, verified against its checksum, and then forwarded, but using more powerful application-specific integrated circuits. Hence, the bridging is then done in hardware, allowing packets to be forwarded at a full wire speed. When a twisted pair or fiber link segment is used and neither end is connected to a repeater, full duplex Ethernet becomes possible over that segment. In full duplex mode, both devices can transmit and receive to and from each other at the same time, and there is no collision domain. This doubles the aggregate bandwidth of the link and is sometimes advertised as double the link speed. For example, for fast Ethernet, we can say that the speed is 200 megabit per second. It's related to duplex. It's a full duplex. The elimination of the collision domain for these connections also means that all the link's bandwidth can be used by the two devices on that segment, and that segment length is not limited by the need for correct collision detection. Since packets are typically delivered only to the port they are intended for, traffic on a switched Ethernet is less public than on shared medium Ethernet. Despite this, switched Ethernet should still be regarded as an insecure network technology because it is easy to subvert switching Ethernet systems by means such as ARP spoofing and MAC flooding. The bandwidth advantages, the improved isolation of devices from each other, the ability to easily mix different speeds of devices, and the elimination of the chaining limits inherent in non-switched Ethernet have made switched Ethernet the dominant network technology. Simple switched Ethernet networks, while a great improvement over repeater-based Ethernet, suffer from single points of failure, attacks that trick switches or hosts into sending data to a machine even it is not intended for it, scalability and security issues with regard to broadcast radiation and multicast traffic, and bandwidth choke points where a lot of traffic is forced down a single link. Advanced networking features in switches and routers combat these issues through means including spanning tree protocol to maintain the active links of the network as a tree while allowing physical loops or redundancy, port security and protection features such as MAC lockdown and broadcast radiation filtering, virtual LANs to keep different classes of users separate while using the same physical infrastructure, multi-layer switching to route between different classes, and link aggregation to add bandwidth to overloaded links and to provide some measure of redundancy. IEEE 802.1aq shortest path bridging. It includes the use of link state routing protocol, ISIS. It means intermediate system to intermediate system, which allow larger networks with shortest path routes between devices. In 2012, it was stated by David Allen and Nigel Bragg. In 802.1aq, Shortest Path Bridging Design and Evolution. Ethernet physical layer evolved over a considerable time span and encompasses coaxial, twisted pair, and fiber optic physical media interfaces and speeds from 10 megabit to 100 gigabit per second. The most common forms used are 10 base T, 100 base TX, and 1000 base T. All three utilize twisted pair cables and 8P8C modular connectors. I will show you how to make that connector later. It's the same as the RJ45 connector, as the regular Ethernet cable. They run at 10 megabit per second, 100 megabit per second, and 1 gigabit per second, respectively. So, fiber optic variants of Ethernet offer high performance, electrical isolation, and distance from tens of kilometers with some versions. In general, network protocol stack software will work similarly on all varieties. Fiber optic allows to reach the data, to transfer data over a fiber optic cable up to 120 kilometers. There are a lot of standards. For example, 10 kilometers, 20 kilometers, 40 kilometers, 80 kilometers, and 120 kilometers. These are the regulated, these are documented standards. Fiber optics has some advantages related to Ethernet, and of course has its own disadvantages. The data which flow through fiber optic cables are protected against electromagnetic interference. The data packet on the wire is called a frame. A frame begins with a preamble and start frame delimiter, followed by an Ethernet header featuring source and destination MAC addresses. The middle section of the frame consists of payload data, including any headers for other protocols carried in the frame. That protocols, usually the upper layers protocols. The frame ends with a 32-bit cyclic redundancy check, which is used to detect corruption of data in transmit. Auto-negotiation is the procedure by which two connected devices choose common transmission parameters, for example, speed and duplex mode. Auto-negotiation is an optional feature on first introduction of 100 base TX, while it is also backwards compatible with 10 base T. Auto-negotiation is mandatory for 1000 base T for gigabit Ethernet connections.